Hi everyone. Simulating stuff is usually challenging. If you want to simulate ants in a tree or something, that's imaginable and possible. But the universe is not so much imaginable. Mark Vogelsberger will have his talk on simulating the universe on supercomputers. Please give him a warm welcome.
The audio is fine, okay. So yeah, I will speak about the universe and simulating the universe, and this is part of my PhD project I'm doing at the Max Planck Institute in Garching near Munich, working on astrophysics. And I will try to explain you in this talk some of our motivations why we run very large simulations on the universe and what we can get out of it. And at the end I will also talk a bit on numerical techniques we use to simulate these things. So my general overview is something like this. So first of all, I will give you typical length scales of the universe and some objects in the universe that are interested, so you get a feeling of the dimensions we're interested in. The second point is then that I want to motivate our work in more detail. And the third point, I will show you very recent simulations we did and simulations that are still running and are soon finished. And then I will focus a bit on scientific output you can get from these simulations. And in the last point, I will explain some methods we use. So first of all, let's look at the playground we are interested in. So this is the Earth, and the typical length scales we are used to are the length scales on the Earth. So the Earth has a diameter of about 12,000 kilometers. And yeah, this is what we are more or less used to. Then the next scale is the solar system, with the sun in the middle. These are about now 6 billion kilometers, corresponding to 20,000 light seconds or 5.5 light hours. So this is our next neighborhood, so to speak. And then the whole solar system is embedded in a galaxy, the Milky Way, you all know. And this is how it looks on the sky. And this is how it looks schematically. So this is now a scale of 10,000 light years. So when the sun is just one star in this Milky Way, and there are lots of other objects, as you can see. And it's a typical spiral galaxy. You can clearly see the spiral structure here. Then the next scale is the so-called local group. The local group is a collection of larger and smaller galaxies, where also the Andromeda galaxy is part of. You can see this here, the Andromeda galaxy. And also the Milky Way and lots of other so-called dwarf galaxies, so these are quite small galaxies. And this is now the scale, this is already 1 million light year. Then the next, this is just an example, the Andromeda as seen from the Earth. Then the next scale is so-called superclusters. So you have to imagine that all galaxies you have in the universe usually cluster together and build clusters. And these clusters again build superclusters. And this is the nearest superclusters, and this is now a scale of 100 million light years. And the next largest scale is then the whole visible universe. This is a scale of 1 billion light years, and in total you have then 3 times 10 to the 22 stars in this whole visible universe. So these are the typical length scales we are used to in astrophysics and we have to deal with. Now, what is the goal of our work, or what we are interested in? Well, the question is quite simple. The question is in principle where we are all coming from. This is the key question. So this is a small animation showing the Big Bang. This is of course not realistic, it's just an animation made by NASA, I think, showing the Big Bang. So this very hot phase. And then you can see that out of the Big Bang, the galaxy formed, the planets formed, the stars formed, so everything formed. And the question is actually, can we describe with physical theories how everything formed, how the structure in the universe formed? So this is the key question of so-called structure formation theories, what we are interested in. And we run the computer simulations and we use other physical models and things to actually understand how the structures in the universe look like. And you can also see in this movie the expansion of the universe, and here you can see the galaxies, and in all these structures we're actually interested. So at the moment we have a standard model for the evolution of the universe, for the structure formation. And this standard model is shown here. So everything started with a very hot Big Bang here. And then you had some quantum fluctuations. And these quantum fluctuations were, so to speak, blown up in a phase called inflation. This is a phase where the universe expanded by lots of orders of magnitude. And then these quantum fluctuations are, so to speak, the seeds of the structure formation, of the further structure formation. So you have a density field of matter, and you have imprinted in this density field small fluctuation, and out of these fluctuations you form everything that is in the universe. And this shows then the whole evolution, and we think today that the universe has an age about 30.7 billion years. And the interesting thing is what we can do today. We can use satellite missions like this WMAP mission and observe the universe at this time. So due to the finite speed of light, we can look in the past of the universe, and if we do such an observation, then we get this result. So this is now the universe about 30 billion years ago, observed by one of the satellite missions, recent satellite missions. And this is in principle a short moment after God actually created the universe. And you can see this is a temperature map of the microwave radiation. So you can see small temperature fluctuations, and these temperature fluctuations are actually correspond to the density perturbations. And from these density perturbations, the whole universe then evolved and grew. And this is a very hot topic, and in 2006, actually, one Nobel Prize, or the subject of the Nobel Prize dealt with this cosmic microwave background. So the question then is, can we actually create a virtual universe from these initial conditions? So we know the initial conditions today very well. And the question is whether we can model the whole thing in a way that we end up with a universe that looks from a statistical point of view like our universe. And the answer is, as we know today, yes, you can do this. So you have to, of course, use a very good physical model to describe the universe. Then you have to write a very clever code and use extremely fast computers. And then you can simulate from this point the whole lifetime of the universe, so 13 gigayears or 13 billion years to what we see today. And this background image is actually the universe at a very early time. And if you then use the computer and let evolve these density fluctuations, so this is now starting from a very early time to the present time, then you can see that these density perturbations we had, that they build these structures. So what you get in the end is very filamentary structure and clusters of matter, and this is called the cosmic web. You see also these voids here that build up, and all is done by gravitation, just because the material just attracts each other, and then it forms these structures. And what I show you here is it's not ordinary matter, what you are used to, it's dark matter. So this is a point I will come a bit later to. So what actually do I mean by dark matter? Well, the problem at the moment is, or what we know about the universe, is that it only consists to 4% of matter we are used to. So matter like the Earth, the stars, or matter we are made of, this only makes in total 4% of the whole energy content of the universe. The largest fraction of the universe is made up of something called dark energy, so 73%. Dark energy was discovered 10 years ago, so it's quite new, and we know today that it makes up the largest fraction. And another large fraction is made up by dark matter. Why is this matter called dark? Well, because it does not interact with electromagnetic waves. So it does not shine, and it does not absorb any light. So we cannot observe it with telescopes or satellites, something like this. And from a theoretical point of view, the dark energy is a quite challenging thing, because if you use very simple arguments from quantum field theory and try to get the correct value of dark energy that we observe in the universe, then you suddenly end up with a value that is 120 orders of magnitude of the correct value that we observe. So currently lots of people are working in this field and develop quite complicated theories to describe this dark energy. For dark matter, the situation is a bit better, because we know that The standard model we have for particle physics is somehow not complete. We know that it needs to be extended, and natural extensions of this standard model actually provide us with a particle that has all the properties that dark matter should have. So dark matter particles, as I said, they only interact by gravitation, and particle physics has some of these particles. And the interesting thing about dark matter is that in the next year, or probably in the next year, in CERN, the LHC, the Large Hadron Collider, will go online, and they are, beside other things, searching for these particles. And also on Earth, we have some detectors to search for dark matter, but currently we haven't yet discovered it. But the point is that it's quite probable that these things will be solved in quite short time, so we are currently living at a very exciting period in science. So in all these simulations I showed, the previous one and also this simulation I will show you, they only simulate the dark matter content of the universe. So they do not actually simulate the stars or something like this, they only simulate the dark matter. And the reason why they only simulate the dark matter, because it's just the largest fraction of matter. So you can, for the large scale structure, you can just ignore the baryons and only simulate the dark matter to look at the structure formation processes. And especially if you search for dark matter on Earth with detectors or something like this, then you have to know how dark matter near the Earth is distributed to get an idea what you are searching for, actually. And this is the reason why lots of simulations do not simulate a large volume of the universe, but focus on an object that has the properties of the Milky Way. So the Milky Way is also surrounded by dark matter, and these simulations then simulate the dark matter halo of these of Milky Way-like objects. And this is a very recent simulation, not done by us, but by a group in the USA. And they used one of NASA's fastest machine to simulate a Milky Way-like object. And here you can see now the dark matter distribution. So this is the density field of the dark matter. And you can see in the inner region you have a very high density, and then you have lots of these so-called subhalos. So this is substructure of dark matter. And what I show you next is a new simulation we are currently running. This is the Aquarius simulation, and it's not yet finished. This is, when it's finished, it's the highest simulation, or highest resolution simulation ever done. It takes about 4 million CPU hours, and the storage you need to store it is about a 50 terabyte output. And this is, again, like the previous slide, the dark matter distribution in such a Milky Way-like structure, and you can now clearly see that you have lots of substructure and a very high density in the center. And as I said, the simulation will be finished at the end of January or something like this. And this simulation actually was done by our institute in collaboration with the Virgo Consortium. So just to show you what the Virgo Consortium is. So these simulations are so large that you actually cannot run them from a single institute. You do not have the money for the CPU hours, and you do not have the manpower actually to analyze all the data. And this is why this group was formed, and they run all these high-resolution simulations. And this is, again, a slide. And if you look how this movie now shows how the final object in this simulation just builds. So you have, again, these small density perturbations in the beginning. And then you can see that due to gravitation, now the structure begins to form. And this started again at a very early time. So there you can see the time scale. And the typical length scale here is also more or less the size of the final Milky Way size halo. So this is now in parsec, so parsec is about 3 light years. And you can see clearly this filamentary-like structure. This is typical for these structure formation processes, that you have this cosmic web. And if you now go a bit further, then you can see that the final object here starts to build. So it builds just by infalling material, and this infalling material gets then tidally disrupted and builds a smooth background, and in the end you have a smooth density background plus some subhalos and plus this substructure. And then you can go even further, and you can clearly see all this substructure orbiting here and getting tidally disrupted and building the final object. And yeah, so on. And this is actually not the highest resolution we are running because this is not yet finished, but this is, I think, 8 times smaller than the final resolution. So the machine we used to do this calculation is the new HL RB machine in Garching. So this is part of the Leibniz Rechenzentrum. The Leibniz Rechenzentrum in Garching is one of the national supercomputing centers in Germany. So another very large one is in Jülich, you might know. And this is just the data of the machine. So it got recently extended in the beginning of 2007. And this is where the machine is sitting. It's sitting in a cube. And this looks like this. So this is actually the cube where the machine is residing. And here's the entrance where you can go in. And this is how it looks from inside. So it's a quite large machine, and yeah, at the moment I think it's still in the top 20 or something like this. Okay, concerning the size of these simulations, they are increasing with time. So you can say that every 17 months the size of the simulations doubles. So this is somehow connected to Moore's law. And quite recently we were running the Millennium simulation. This was not a simulation focused on a Milky Way sized object, but simulated a large fraction of the universe. And we used our own code. This is the so-called gadget code. And you can see that due to some algorithmic tricks, we somehow broke the general trend and could run even higher number of particles compared to this general trend. And this Millennium simulation actually, as I told you, is a simulation of a large fraction of the universe. So this is now a very large scale. And it has a very large dynamic range because we can now zoom in. So this is again this dark matter distribution and this filamentary structure. And we now start to zoom in to one object. And you can see from the scales we are now already at megaparsec. And this is also the key problem of all these simulations, that you have an extremely large dynamical range. And here we now zoom in into one of these dark matter clusters. And again, a Milky Way-sized galaxies or the local group would actually sit in one of these dark matter halos. So you can say that all the baryonic matter, like the stars and the galaxies, actually always trace more or less the dark matter distribution. And this is again a reason why we only run dark matter simulations. And it's also, from a computational point of view, dark matter simulations are a lot easier than simulating stars and gas and all this, but this is something I come to a later point in the talk. So now you can see we have a scale of 15 megaparsec, and the final scale will be about, I think, 3 megaparsec or so. So you can again see all this substructure and the central region of the, so here the dark matter density is then extremely high. Okay. So this simulation was running on a machine of the Max Planck Society. This machine is now a bit outdated, so to speak, but it gets soon extended. So this took only, so to speak, 350,000 CPU hours and was running on a 512 cluster within 1 month. And there you can also see the number of floating point operation and all these. So it takes a quite large number of processors to run these simulations. And here are some other machines we use. There's one very funny machine in Barcelona that was actually placed 9 in the top 500 in June of this year. This is the Mare Nostrum machine. It's placed in a church. I'm not sure why, but they say it's due to cooling reasons, so I'm not sure. I'm not totally sure. So this is this picture here. And very recently, a French group was running a very large simulation of the universe. I think it's at the moment one of the largest. And this was running on 6,000 processors on this machine. Then we also use this NASA machine. This is the Project Columbia supercomputer. And we have other nodes in Paris, Durham, and the Max Planck Society Rechenzentrum. And for testing and smaller simulations, we have, for our work group, a smaller cluster of 500 CPUs just to make debugging and all these things. But most of these machines get updates in the next year. So now I showed you lots of movies, nice movies, and you can ask what can you, from a scientific point of view, get out of it? Because science is not about making movies. So the scientific output you get is quite large. And the reason why it's so large is that we cannot, as people working in astrophysics, we cannot do any experiments in laboratories. It's just impossible to do experiments like people in quantum physics or solid-state physics do simple experiments. This is not possible for cosmology and astrophysics. So we have actually the only tool to analyze models and to say whether models are correct or not is to run these very large simulations. And yeah, so this simulation also have an extreme public impact because lots of people are interested in it, and so we got lots of TV stations and newspapers and radio stations reported on this Millennium simulation. And due to the scientific impact and due to the public impact, we have the chance actually to use all these supercomputers, because otherwise we would have no chance to get millions of CPU hours on all these machines. And this is now one of these so-called public videos where you have a fly-through through this Millennium simulation. And actually, I'm not sure whether this was the video or another one got a prize only for the visualization. So this is just a fly through the dark matter distribution, and you can see this is now again a fly around one of these dark matter objects. So it's of course no science, but it's nice to look at it, and you can get a feeling for the structure in it. The science you want to do is a bit different. So we can observe with telescopes and satellites and all these things, we can actually observe how galaxies are distributed in the universe up to a given distance. And if you make for each galaxy a dot in a diagram like this, then you get structures that look like this. So every dot here is a measured galaxy, so to speak. And if you look at this structure, especially here, then it reminds you somehow on this filamentary structure of the dark matter distribution I showed you before. And the reason for this is that galaxies actually trace, as I said, the dark matter distribution. And now the question is, if we make the same map, not based on observation of the real universe, but construct a map based on the virtual universe, we simulate it. So how does it look? And the question is that this is now a comparison between a real universe, so our universe, and the virtual universe we created in the computer. And every dot shows again the distribution of the objects. And in principle, from a statistical point of view, you just cannot tell what's the real universe and what's the virtual one. So it seems that our theories and the structure formation in the computer that we get out seems to be correct, or more or less correct. And what you can also do is you can analyze single objects, these dark matter halos I showed you before, and look for density profiles, so how the mass and the density in these objects is distributed. And then you get, also this was only found by simulation, a universal profile, this so-called Navarro-Frank-White profile that was found by these people 10 years ago, also based on simulations. So this is now the distance from the center of the object, and here you see the density of the dark matter distribution, and you find for all of the objects in the simulation, you find this universal profile. And it was not known before, it's just a result of all these simulations. And if you now look at the Aquarius simulation I showed you before, this world record simulation, and then again look at the density profile, then a very important question is whether your results are converged or not, because we run the simulations with different number of particles, so with different resolutions, and it's very important that the density profile, for example, you get is converged. And as you can see, this is the case. So we are still waiting for this simulation. This is still running, but it will be finished quite soon. So the reason why this, even the highest number of particle simulation is in this plot is that this plot is not at the final time of the current universe. It's still a while ago, so to speak. So these are just some applications of science you can get. And what I show you next is that we cannot only simulate cosmological things, so the whole universe or a large fraction of the universe or a Milky Way-sized object embedded in a cosmological universe. We can also simulate single objects like single spiral galaxies. And this spiral galaxy actually does not only consist of dark matter. You have stars, you have gas, and you have all these things. And you can have interaction between galaxies. For example, here I show you a picture where two galaxies actually merge together. And the question is whether we can also simulate this, because for this we have to take into account the stars and the gas and all these things. We cannot only simulate the dark matter. And this is also possible, so we can build quasi-equilibrium objects. They consist of these components, so you have a dark halo surrounding everything, then you have a stellar disk, for example, for a spiral, then you have a central bulge of stars, and you have a gas disk, and as we know today, most or nearly all galaxies have a supermassive black hole in their center. We can also simulate this. And if you put all this together and then run these quasi-equilibrium models, then you can here see, for example, the gas distribution. You can clearly see that we get the spiral structure correct. And also if we now tilt the whole thing, then you can see that we have a quite thin disk. So this is called the face-on view, and if you look at it edge-on, then it's called the edge-on view. So we can also simulate these single objects. And since we can simulate these single objects, we can also simulate the interaction of these single objects. So we just take two of these objects, let them merge, and then ask whether the output from the simulation looks like the observation or not. And this is now shown here in this movie. So this is now a collision of one of these objects I showed you before. I will only briefly mention this. So these are again two spirals. And here's the typical length scale. And then you can simulate this merger, and then you can ask whether this looks like the observation or not. And these are also applications. So these are, so to speak, isolated simulations that do not need any cosmological box around them. You just take the objects as quasi-equilibrium objects and then let the simulation run. Okay. And the point is that these simulations, because they include the gas and the stars and all these things, they are, from a computational point of view, they cost you a lot of CPUs and CPU hours. So this is the reason why, in principle, you cannot run these simulations for a large cosmological box, so for a large fraction of the universe, because it just takes too much time. What else can we do with simulation? Well, I show you one more application. So I told you that dark matter cannot be observed because it does not interact with light, so to speak. But there are certain candidates for dark matter particles that can self-annihilate. This means two particles hit each other and then they just radiate something away. And what they, for example, could radiate is gamma rays, so very high energy radiation. And then we can put today satellites in the sky that search for gamma rays. And then the question is whether, if the Milky Way is surrounded, from our understanding today, by a large fraction of dark matter, then this dark matter, due to the self-annihilation, should shine some gamma rays, and we should, in principle, be able to observe this. And this is now the gamma ray sky that would be observed by a virtual satellite surrounding the Earth in a virtual universe that we simulated. So this here, where you have lots of radiation, is the center of the galaxy, because I showed you before that the density is very high. So you have lots of dark matter, and then you have lots of self-annihilation, and then you have lots of gamma rays, and the satellite, in principle, could observe this then. At the moment, we have no, or there are some hints that we could have observed something, but it's not sure at the moment. So we are still waiting for definite proof that we can observe something like this. And when you remember one of the last slides where I mentioned this GLAST, so GLAST is a satellite that is going to be launched in the next year. And one of the tasks of GLAST is to search for this gamma ray annihilation. These are then called indirect dark matter detection experiments. So the next thing I want to show you is not so more on the results we got, but more on the methods we use to do simulations. And I will focus on dark matter only simulations. So this means we have two leading things in the simulation. So we have, on the one hand side, gravity. So every particle in the simulation interacts with every other particle by gravity. And this means gravity in the framework of general relativity. So we have an expanding space and then gravity there. And Yeah, this is the one part of the simulations, and the other part of the simulation that is a lot more complicated to simulate. These are the so-called hydrodynamic processes. These are all the gas and stars things, and there you can see you have lots of processes like shocks, radiation, star formation, supernova, black holes, and all these things. You have, in principle, simulations can do all of this today, but the modeling of these processes is quite complicated, and there are a lot of uncertainties in these processes. So for the rest of the talk, I will focus on the gravity part. And in principle, if you are interested in the largest scales of the universe, then the gravity is the only relevant force, because the hydrodynamics become only relevant if you go to galaxy-like scales, so to smaller scales. And the gravity is done by what is known as n-body integration. So we represent the dark matter particles, so the dark matter fluid, so to speak, by a finite set of particles. And then we evolve these particles under the mutual gravity, taking into account the expanding space. And this gives you, in total, a system of 3 n-coupled linear differential equations, and you have to solve these equations. So the code we use is, I also mentioned this, is the gadget code. This code started as a PhD project of Volker Springer. This is the main author. And currently the public version is 2, so you can download it from this website. And the internal version is 3. And the main difference between internal and public is that the public version only has a very limited set of physical models and features in it. So the internal version has a lot more features. But for simple simulations, also in principle, you could run the Millennium simulation only with a public version in principle, if you have a machine that is large enough. And so this code was actually used for the Millennium, for the Aquarius, and all the other simulations our institute is running, and it's standard C code, and it is about, at the moment, 75,000 lines, the internal version. And since we have to run these simulations in parallel, we use standard MPI, and for FFTs, we use the FFTW library that has a nice MPI interface also. And we also use the GNU Scientific Library, but only for some initial integrations. So in principle, we could skip the GSL and program the integrations ourselves, but we have used the GSL. So let me come back to the dark matter simulation only. So how we solve this? Well, I said that we represent the dark matter by a finite set of particles, and this is why these codes are called n-body codes. So one key point you have to take into account is that these particles in the simulation box are not single dark matter particles, because these dark matter particles are like electrons or something like this. They are extremely light, and you cannot simulate them because you have just, the number is so large that it's just impossible to simulate all of them. So what we do, we take a clump, so to speak, of all these particles and as representative, and then simulate only clumps of these dark matter particles. And if you do so, you have to modify your force law. You cannot use the simple force law for gravity. So the simple force law would be take a gravitational potential like this, skipping this away, and then calculate the force just by this second-order differential equation. This does not work because we do not simulate every single dark matter particle. And since we simulate these clumps, we have to soften the potential. And this softening parameter, that's usually called epsilon, just gives you the correct behavior of these clumps with respect to the dynamics of the dark matter. And this softening is actually a very crucial parameter if you run all these simulations, and you have to choose it quite wisely. So what you then do is you take this set of differential equations and just evolve your system in time. And now the question is that you have a finite set of particles, so n particles in your simulation to represent the dark matter. And this n has to be very large, and this is also the reason why the simulations are so expensive. And why does it need to be so large? Well, the larger the n, the smaller the mass of these individual clumps, and the smaller the mass of the clumps, the better your resolution for smaller objects. I mean, it's clear, if you want to resolve an object of 10 to the 6 solar masses and have only clumps with 10 to the 7 solar masses, you just cannot resolve it. So you want your clumps to have a very small mass. And this is why you have to increase the number of particles. But on the other hand, you want to simulate a large volume of the universe to have a representative set of data. So in the end, this means that you have to choose a very large n to do these calculations. And this is why the simulations of only dark matter are also so expensive. And the most expensive things of these simulations is calculating the forces. And why is calculating the forces so bad? Because gravity is a long-range force. So we cannot just say, okay, we have a particle here, and then only look at its surrounding and calculate the forces. We have to take into account all the particles that are in the box. And this gives you then normally a problem that scales like n square. And this is, of course, a very bad scaling, because we are interested in particle numbers like 10 to the 7 or 10 to the 8, and then it's just impossible to calculate anything. So this is the main problem for the force calculation. And you have somehow to find a way around this to calculate the forces. And one standard way around this is to use so-called mesh methods. So the principal idea is that what we need is the gravitational potential at a certain point in the box. And those of you who know a bit more about physics might know that the gravitational potential, you can get this out from a Poisson equation, so a second-order partial differential equation. And if you transform this Poisson equation to Fourier space, then you get a simple algebraic equation like this. And from this simple algebraic equation, you can then get the potential a lot easier if you just Fourier transform and then back again. So this is, so to speak, one way to calculate the potential. And in principle, it looks like the best way to do it, because the FFT can easily be parallelized, and it has all the features you need. But it has also some shortcomings, because you have in your box a finite size mesh for the Fourier transform, and then it's clear that you cannot resolve structure that is smaller than the mesh size. You're just limited by the mesh size. And you cannot make the mesh that fine to resolve every structure, because then it just takes too much memory and is too slow. So you cannot do this. So you're in a certain region limited, so to speak. And now there are two ways around this. On the one hand side, you can, of course, say, okay, if I have a region with a very high density in my simulation box, then I just do a refinement of my mesh and make it finer and finer, just in an adaptive way. These are then so-called adaptive mesh refinement codes, and they are also very popular for cosmological simulations. But you can also use a different method, and this is called the tree method. So the idea of the tree method to calculate the forces is very simple, because if you have a particle at a given point in the simulation box, and you want to know how the forces do to a group of particles far away from this particle, how strong this force is, then you can in principle group the particles that are far away together to one particle that has the mass of all the particles together. And as the position, you take the center of mass position of this group, and then you can just calculate the forces between these two particles then. So this means you just represent a whole group by one particle, and then this reduces the scaling of the force calculation to a lot better n log n. So, and the grouping and all these things is done by octree-like structure. So this is shown here. So in the beginning, this is now in 2 dimensions, you have a structure like this, and yet then you divide the whole time, and you divide so long until you have in each of these squares only one particle left. So in 3 dimensions, this would mean you divide until you have in one of these cubes that you form by just dividing only one particle left. And then you do the force calculation in a way that you run this tree downwards, and by a certain criterion you say, okay, I do not want to walk the tree further, I just stop here and take the force of the whole group and not of single particles. And this then gives you in the end this n log n. And this is also the reason why this method is called tree, because if you look at it, then it looks like a tree with smaller leaves and lots of branches. And this method is very popular. So with this method, you can also quite efficiently calculate the gravitational forces. But it has also some shortcomings, because if you're at a very early time of the simulation, then the density field of the dark matter is very smooth. So you do not have very high density regions or so on. And then to make the tree method very accurate, this again takes a lot of time, because then you have to walk the tree for quite long times, and this is quite inefficient. And so the best you can do is you combine the mesh method with the tree method. So the mesh method breaks down whenever you want to resolve small scales in high density regions. And this means that you just can cut your force in a long range and a short range part. This is shown here in Fourier space. So you have a short range and a long range part. And you put to the long range part an exponential cutoff in Fourier space. And then you can calculate the long range force just by a particle mesh method I showed you before. And this short range thing, you can just, with this modified gravitational potential, calculate with the ordinary tree. And in the end, you put both forces together and have the total gravitational force. And this is actually the method that was used for the Millennium and gave this a lot better scaling compared to other simulations at this time. So this is the so-called TreePM method, and it's a quite standard method. So the next thing, if you have calculated all your forces, then you have, of course, to evolve your system further in time. And what you want for cosmological simulations, you want to have, of course, a very fast integrator, because we do not have, it takes otherwise too long. And what you also want to have is, you want to have an integrator that is stable if you integrate lots of orbits. Because I showed you in the movies that you have clumps orbiting in these final structures, so they are doing lots of orbits, and you have to have an integrator that actually captures this behavior correctly. And if you look around in literature, then one of the best integrators you can find is the so-called leapfrog integrator. So it's a very simple integrator. You have these steps. So you have a velocity step and a position step. And you just evolve the system by this simple rule. And this is a second-order accurate algorithm, but this is not the most important thing. The most important thing for this algorithm is actually that it is symplectic. And this symplectic feature implies that you have a very good energy conservation. So if you look at the standard Runge-Kutta method of second order or fourth order or even higher, then you will always have this. So this is now the energy, and here's now the number of orbits. Then you will always have a secular motion in the energy, in the total energy of the system. And normally, of course, the energy should be conserved and should be constant. And so it's especially very unpleasant if you have a secular drift. But if you look at the leapfrog, in this case, then you have oscillations, small oscillations, but you do not have any shift in the energy. And if you look at the orbits of particles that are orbiting around a center here, then you can clearly see that, okay, you have a shift here in this position here, but you do not increase the size of the orbit, so the energy stays more or less constant for the leapfrog. And this is not the case if you use the standard Runge-Kutta methods. And so nearly all cosmological codes use this leapfrog method, and it's those of you who are used to maybe molecular dynamics simulations, this leapfrog method is quite closely related to the standard Vallée algorithms for these kind of simulations, and this is then also symplectic. So the symplectic character actually gives you the correct energy conservations, more or less, for these algorithms. And this is the most important thing we need. So for the rest of the talk, I will show you some new ideas, some very recent new ideas we developed to get even more resolution in these simulations without needing more particles. So this is now a quite new concept. So the key problem is that if you have a detector for dark matter on Earth and you want to know how dark matter is distributed on the scale of this detector, so the detector has a size of some meters or so, it's very small, then if you use standard simulation techniques to actually analyze these scales, then you would at least need 1,000 billion particles in the simulation. And the highest simulations, this Aquarius, has now something like, you can guess, from 85 million times 15 particles. So it's a lot. It's at the moment absolutely impossible, and it will be possible maybe in some years, so maybe in 20, 30 years this will be possible. But the people running the detector experiments want some answers yet, and so you have to develop a new method, and this is now a new method to get more resolution in the dark matter fluid. And the key idea is that we use what I called virtual particles. So this is a concept that is based, you have a dark matter particle in your simulation at this position here, a real dark matter particle in the simulation, and then you imagine a cloud of virtual dark matter particles that are actually not simulated, but you imagine them around this dark matter particle shown in blue here. And then you ask how this cloud of virtual dark matter particles around the real dark matter particle in the simulation, how this cloud gets distorted, how it gets stretched, and so on. So you can see if you go in time from this position to that position, then this cloud just gets bigger. And we search a way to follow the evolution of this cloud. And if we can follow the evolution of this cloud, then we can say how the very local density around this particle actually behaves. Because if the cloud gets stretched and gets bigger, then the density in that region must go down. If the cloud gets smaller, then the density must go up. So this is the principal idea, and we can attach such a cloud to every particle in the simulation. And then we can get a lot higher resolution just by solving the distortion of this cloud. And you can solve this equation for the cloud. This is then a bit more complicated than the standard equation of motion. This gives you then a tensor differential equation. So in principle, this means this is a matrix, this D, and this T is also a matrix. It's a 6 × 6 matrix. So this means you have to solve, in the time integration, 36 additional coupled differential equations. This sounds a lot, but if you do it, then it's a lot faster than just increasing the number of particles. Because the most expensive part of the calculation is the forced calculation. Okay, so this is a very, very recent method, and we are currently implementing this this is already implemented in the gadget code in the internal version. And with this method, then, you can actually analyze dark matter on the scales that is relevant for detectors or for these gamma ray satellites and all these things. Okay, now, since I showed you lots of things and lots of supercomputer simulations and all these things, you might come up with a question whether you can simulate the universe with your own laptop or if you have a small cluster at home or whatever. And yeah, in principle, this is possible. So, of course, you cannot use the particles numbers we used, but the gadget code, the public version, comes out with some simple examples of initial conditions. For example, this pair of colliding galaxies, or cosmological structure formation with gas. This is all included as some examples. And what you can then do is you compile the code. Maybe you have to adjust some of the options of the makefile, but this is all well documented. And then use a certain parameter file as the input, but they are also part of the public version. And then in principle, you can run it. So I'm not sure how long it takes, but I think the examples can all be run on a standard laptop within some hours. So, and then you get in principle, at lower resolution, the same output we get at higher resolution. So you should be able to run this. And it also includes some IDL scripts to visualize the results. I mean, you can then see the dark matter distribution and all these things. These IDL scripts only show you the particles, so it's not like in the movies I showed you, you have no smoothing or something like this, but to get an idea of the principles, it should work quite well. Okay, and that's it. Thanks. Okay, questions?
Hi there. Thank you very much for the talk. A couple of questions. Firstly, very simply, how many people are involved in the development of the software that you're using for these method simulations? And secondly, do you have some sort of metric for measuring the accuracy that you lose by doing the different things to calculating the gravity? Do you use some sort of metric to say how much you've lost in the various trade-offs you make?
Well, concerning the second question, the typical I mean, if we cut the force calculation just by a tree or so, then we lose something in the order of some percent on accuracy. But this depends also on the parameters, how you run the tree, because you can specify in the code how far you want to run the tree. If you run it further, then of course you have a higher precision. So in principle, you can run it exactly the tree, and then you have no error at all. But we cut it usually at a percentage level or something like this. So in the first question, I didn't get somehow, so it's...
Just how many people are involved in the software development side of it for the simulations you're running for the Millennium project or for this new one?
So you mean whether these are free codes or not? Or
No. How many people are...
how many people? Well, the gadget code started as a single-man project. And then 3 years later, 2 other people joined in. And at the moment, at the further development of the code, I think we had 10 or 15 people working on different aspects. So there are people working on radiative transfer where you want to know how radiation is just evolved in the gas and all these things. So 10 to 15 people are currently working on this. So this is the typical amount. Other questions?
You started out by telling that dark matter is yet to be discovered, and then you start telling about simulating it. So what are your assumptions about the nature of dark matter when you simulate it?
Yeah, well, okay, the assumptions about dark matter are twofold. The first thing is that we think today that dark matter is cold. Cold means that at the time when or at very early times of the universe, the motion of the dark matter was not relativistic. It was very slow, so to speak, the velocity. This is the first assumption we have. We think that it's cold dark matter. And the reason why we think that it's cold dark matter is if you use a model of dark matter that is very fast in the beginning of the universe, then you can imagine then you cannot build up small structures because the particles just blow away. So what we think today is that we have cold dark matter, so nearly zero velocity dispersion at the beginning of the universe. This is the first thing. And the second thing is that dark matter behaves collisionless. So collisionless means that if you have 2 dark matter particles, then they do not scatter with large angles, for example. We think that it behaves like a collisionless fluid. And the softening I showed is another reason for the softening is that you have actually this correct collisionless behavior of the dark matter. So these are the 2 main assumptions we put in for the dark matter.
Do you use some special code for some special CPUs, or it makes no sense because you have too many access to different machines?
Yeah, right. So, so I can tell you about the internal makefile. So the internal makefile, I think, is tuned for about 10 or 15 architectures. So the code was running on Craze, on whatever. So but this is the main part where Volker is working on. So he's tuning the code for the different architectures. And yeah, but in principle, you can choose just for the public version, for example, simple GCC to compile it, and then you can run it on just a laptop. So, but in principle, we running it on lots of architectures, and you have also lots of problems because the MPI library. Especially when new versions come out, we sometimes have large problems with the MPI libraries because the amount of data we transfer between different processes is so large that we easily have problems. But yeah. Okay.
Thank you. You showed a diagram in the beginning which shows the beginning, and then it expands in a tubular form, and that suggests that it's expanding.
Yep.
Does your simulation start in the same volume and stay in the same volume, or does it...
Yeah, this is a good question, actually.
And this original picture, it suggests that the expansion is not uniform.
Okay, so first of all, the expansion it's not uniform, because, for example, if you look at the dark energy I mentioned, you see dark energy was discovered because in the late time of the universe you have a phase where the expansion goes faster. It's just an acceleration of expansion. So it's not uniform, the expansion. And how do we treat this in the code? Well, in the code, we go actually to a different coordinate system. We do not use physical coordinates in the code. We, so to speak, rescale all the length scales in the code by the current size of the universe. So we are working in what is called co-moving frame. So if we start with the code, and at the end time, the volume has always the same size in the computer. But if you want to have it in physical coordinates, then you have to rescale this with the current size of the universe. And this is just, you can rewrite all the equation of motions from general relativity in a way that you have only equations that are in this co-moving frame. And this is the frame we use in the simulation. Okay.
Have you considered using a distributed computing model similar to BOINC or SETI?
Not yet. So,
are you considering it for the future?
As far as I know, not. I mean, the main problem is, I'm not so in this distributed things, but we need to have very fast networks to transfer the data between the nodes. This is a limitation then, of course, because we need really high-speed connections between the nodes. At the moment, we use, or most of the machines use InfiniBand connection, and these are extremely fast, and I do not know whether this will work with distributed computing, so it's not clear.
Most people have broadband now. I think it's a strong possibility. I mean,
yeah, but I think even broadband is not fast enough. Maybe.
Yeah, I realize the trade-offs, but there are some at Carnegie Mellon, I'm sure you know, who are experimenting with this and claim it could work faster over time.
Okay.
I'm not sure if you're aware of that.
Actually not, no. But, I mean, maybe in the future this will work, but at the moment I think it's no alternative, because it's...
I'm afraid that models similar to SETI won't work, because if I understand correctly, after each step, all nodes must have all information about entire universe, so you would have to put information, or at least about some subtrees, if you are still optimizing it with tree. So you would have to put enormous amounts of data to all clients. So
yep.
it could be limitation of models similar to SETI.
Just a comment on the BOINC idea. Well, the sheer speed is not is just a part of the problem. You need extremely low latency links, so it's not possible to go BOINC.
Further questions? Okay. Nobody, I guess.
Did you use your code to simulate into the future? So say that you can predict how the universe will look in 1 billion years?
Yeah, right. I mean, you can do this, but I have actually no experience with this. Of course, you just do not stop at our age and just let it evolve further. So it's, yeah, you can do it in principle, but these simulations all stop at recent time, and I do not know much about other simulations. I mean, I'm pretty sure that people are doing this, but because we are interested actually in saying that our models are correct, and since we can observe only from today in the past, we are actually not running them in the future, but of course you can. You just let them evolve further. Okay. So, are we finished, or?
One last question, maybe?
Okay, then we are finished. Thanks.